Welcome. This presentation covers assignment 5 for the mechanism sessional. We are presenting railway ladder system for our group project.
We'll start with the problem statement and the way of approach we did here. Also, we are going to satisfy the Grashof criteria to ensure the smooth movement, avoiding the double cranking situation. And then we'll go to the kinematic analysis where we talk detailedly about the displacement analysis, velocity analysis, and acceleration analysis. And then we are going to present our CAD model, which we have done in SolidWorks, in the railway ladder system. And also, we are going to talk about the problems we faced and the solutions we came up with.
This project was done by the following group members. Our problem statement is to design and simulate a railway ladder system. This system is intended to provide easy and safe accessibility to train coaches from platforms of varying heights and levels. The goal is to synthesize a functional mechanism and create a simulator. Our approach involved several key steps. First, we made reasonable assumptions about the distance between the platform and the train, as well as the dimensions of the stairs. Next, we defined the open and closed positions for the ladder. We then used graphical synthesis to determine the necessary link lengths for the 4R mechanism. Finally, we designed and simulated the complete model in SolidWorks.
To ensure proper movement in this mechanism of railway ladder system, we applied Grashof criteria for a 4R mechanism. The criteria states that sum of the longest and shortest links must be less than or equal to sum of the other two links. In our design, the smallest link is adjacent to the ground link, classifying it as a clanker rocker mechanism. The maximum and minimum lengths were 120 and 260 mm respectively, approximately also, satisfying the condition. For synthesis, we defined the dimensions for each stair thread to be 300 millimeters by 800 millimeters with a thickness of 20 millimeters. In this slide, we are going to start the kinematic analysis of our model, which is railway ladder system. So we'll start with displacement analysis, and then we'll go to velocity analysis, and then we go to acceleration analysis. Yeah, now we are using closed loop vector complex number method to solve this. So by taking these two equations and solving them, we'll get the displacement analysis and we'll know the location of all the points. And the next slide, here we differentiate the previous displacement analysis one, and we'll get again two equations, and if we solve them, we'll get the velocity analysis of each point, which is theta1 dot and theta2 dot. We'll get them, and then again differentiating the velocity analysis components, we'll get the acceleration analysis, from which we can solve them and we can get the theta1 double dot and theta2 double dot. Yeah.
These are the CAD components for the railway ladder design system. From here, Navdeep will continue.
This consists of many parts. Mainly, we have used a platform here, which is highlighted. Then this staircase, which has been connected to other staircase using the links of two sizes. One is a long link and another is a short link. And then we have made the ground link, which is fixed, which you can see, which has been like highlighted here. This whole long link is the ground link. Then this ground link is connected to this link, which you can see, which is like a shaft within which there is a linear actuator. This is the linear actuator which moves front and back in order to retract and extend the staircase. When we try to extend the staircase, what you see is as follows. The staircase completely retracts from its original position which is this is the original position, and then it retracts when the linear actuator is moves forward, as you can see. This is the same in the isometric view. So now let's move on to the mechanism and its working. We have used a double rocker mechanism. There are two dead center configurations which are noticeable here, due to which any of the links do not completely rotate but rotate up to a certain angle, beyond which they attain the double center configuration, so as to limit the total movement of it, as you can see. The ground link is the longest link that we have in the mechanism, and this is the shortest link, which can be treated as a rotor. This is connected via the ground using a coupler as shown, which is the linear actuator. This is how our mechanism works.
Initially, we started with right angle triangle approximation in which dead center configuration is involved. For this, the dimension of train frame is taken as 259.81 mm, crank length as 75 mm, coupler as 225 mm, and finally rocker as 150 mm. In the picture, we scale down it to 5 times. So based on our dimensions, half of the stair overlaps with the adjacent side when considering with dead center position, which could cause passengers to stumble. This is the structure of the ladder in open position, that is when it is being used. Here we can see that mechanism is in one of its dead center configuration. The 4R linkage present in this figure is labeled as O2O4BA. Let's see how it works. This is the initial configuration of links. Initially the crank is in rest at an angle of 165 degree. We rotate it up to 19.2 degrees to get to extreme position, that is when the ladder is completely open. This is the configuration when the ladder is open. Here O2A and AB looks like a single link making a dead center. Here are the ideas to improve the mechanism for effective usage. We can attach proximity sensors which detect platform elevation and linear actuation to adjust operator shaft, mechanism to attain an inclined plane to board passengers on wheelchair. Add an interlocking system with sensors that ensure the ladder can only be deployed when the train is stationary. Integrate LED step lighting for nighttime visibility and indicator lights that notify passengers when the ladder is safe to use or is in motion.